In this video, I will cover a numerical technique for computing approximate Shapley values. These are powerful quantities that can be used for explaining how any machine learning model works in understandable terms. I will start by covering the motivation for using approximate Shapley values, and then walk through a mathematical description of the algorithm we'll use here. Now, to make things more tangible, we'll then work through an example in Python. All coding shown in this video is done in a Jupyter notebook available on my GitHub. You can find a link to this notebook in the description below. In my previous video where I introduced Shapley values, I covered the classic definition for these quantities as they were defined by Lloyd Shapley in the context of game theory. Now, for machine learning, we can use Shapley values to determine the relative contribution of each input predictor feature to a model to the resulting prediction from that model. And so in this case, we can gain an understanding for how the model works by seeing which features are most relevant or most important for that model to arrive at its predictions. Now, at the end of that original video, we covered two issues which prevent us from using this classic definition for practical machine learning problems. Let's go over these 2 points now. So the first is that the classic definition requires us to iterate over all possible permutations, including subsets, of the set of input predictor features. And so as the total number of input predictor features increases, this number, the total set of permutations of all the different subsets of the input predictor features increases exponentially. And so this just takes a lot of time to compute and just makes the whole process impractical to achieve. So that's the first point. The second is that we have something called a value function in the classic definition. And this requires us to retrain our model every time we make a call to this value function. Now, retraining the model is impractical because A, the model may not function on a subset of features. Remember, we're iterating over all the possible permutations of the input predictor features, including all the different subsets of those features. So that's one issue. And the second thing is that the training times can be quite long. And so that also doesn't make this a very practical approach. And so because of these 2 points, what we want to do is to come up with a numerical technique for estimating Shapley values that also gets around these 2 points. So that's what we will cover now. So now we'll go over the procedure we'll implement later in Python. As you can tell, we're already in a Jupyter notebook. And as I mentioned before, this notebook can be found on my GitHub, and I've got a link to that in the description below. So in short, the Shapley value, which is this quantity here, phi I, where I is our feature of interest that we are computing this value for. The formula that we're going to follow for computing this is shown right here. So what we're going to do is we're going to sum over some integer value m, and we're going to sum over this difference. Now this difference is the model output. Our model is f, and we're going to sum over the difference between these 2 constructed samples, x subscript plus I and x subscript minus I. And we're going to sum over all these differences and then divide by the total number of iterations. And we can also express this difference as just phi superscript m subscript I. So yeah, as we mentioned, f is just the predictive model, m is the integer number, and this is essentially a hyperparameter to our procedure. And then we have these two constructed samples. Now, what exactly is going on with these samples? Well, in short, the subscript plus I includes the original value for the feature we're looking at, whereas subscript minus I replaces the original value of the feature we're looking at. Now, this is still a bit cryptic, so let's actually just work through the procedure we're going to follow, and that will shed more light on what these constructed samples are. So our procedure is this 3-step process here, where most of the work is actually done in step 2, and I've broken that down into steps A through F. So we start by setting up our various parameters. So what we do is we pick the number of iterations we want it to run for, which is M. We select out the feature that we want to analyze, and that's I. And we also select a sample of interest, and that's little x here. And this is one of the samples that we can take out from the total predictive data set, which is big X. So remember, if you remember from the previous video, Shapley values are always computed with respect to a given sample. What we want is to see for that particular sample which features are really driving the model. So that's essentially how we compute these values. So now at step 2, what we're going to do is we're going to iterate m times, and we're going to work through steps A through F. So the first thing we're going to do is we're going to draw a random sample from X, the total predictive data set that we've got. And that random sample is going to be Z here. Now the next thing we're going to do is we're going to compute a random ordering of the set of features in X. So we're just going to arrange these features around at random in different ways. And the next thing, so now we're at step C, is we're going to reorder the features in samples X, that's our sample of interest again, and Z according to this new ordering that we just computed in the previous step. So now that's going to be X and Z of superscript O. And that just shows that these two features have been reordered in this way. And now steps D and E, we're going to construct our samples. Now we can see what we're talking about here. So these constructed samples are essentially a combination of the feature values in both X and Z. And what we do is for D, which is the subscript plus I, the feature of interest I, wherever that may be in our ordering, the feature of interest and everything to its left is kept as it is in our sample of interest, and everything to the right is then replaced by the values in Z. That's essentially what we do. The only difference between step D and E is that in the case of E, our feature of interest is also replaced by the values in Z. And of course, everything to the right of it is also as it is in Z, whereas everything to the left is still kept as it is in the sample of interest. So this is essentially how we compute these constructed samples, and then we reorder them back into the original ordering so that we can feed them into our models, and that's at step F. And then we compute this difference and then sum over the differences and divide by the total number of iterations. And that's step 3. Now you might ask yourself, why are we doing this? This actually seems kind of complicated. It might make a little bit more sense and might be a little bit more intuitive if we are interested in what the impact is of feature I. Perhaps we could just hold all the other features in our sample constant and just vary the value of I. That might be a more intuitive approach. Now, there's a couple problems with doing that. The first thing is that you can end up with samples that are just not realistic. And we need to mitigate for that in some way. So, what we do here is we are changing groups of features together. And in that sense, we mitigate the possibility of having unrealistic constructed samples. It's not 100% that we can produce an unrealistic sample in this way, but we do mitigate it. It is better than the simpler approach of just holding everything constant and varying I. The other point that we have to keep in mind is that it can be that our feature of interest can work together with other features in our data set to have certain effects on our model. And we don't capture those effects if we're just holding everything constant and varying I. So by having groups of features changing together, we mitigate the effect of ignoring how combinations of features affect the model output. So all in all, this is a much more robust approach for computing approximate Shapley values. And this is why we do it in this way. So now that we have our method defined, let's work through an implementation in Python. So the first thing I'm going to start is by running a cell that will import all the packages that we'll use later on. Let's just import this. And now I'm going to create the exact same data set that I used for my previous video where I introduced Shapley values. So I'm just going to make a simple regression data set, and this is going to be a very simple data set. We're only going to have 3 predictor features and 10 samples, and that's, you can see the data right here. I can also show the targets that we have. Yeah, that's pretty much what we would expect. So just to help with the analysis later on, I'm going to standardize these data just using standard scalar. So that means that each of the predictor features will have a mean of 0 and standard deviation of 1. The next thing I'm going to do is just try to model these data with a simple linear regression. So I'm going to declare that model instance and train it right away. So we have that covered. And now let's work through the implementation of our algorithm. And this is going to be done through 3 different functions. So the first one, construct sample, does as its namesake would suggest, it constructs our samples. So if we go back up and we look at our methodology here, what it's doing is step D and E. We're constructing these artificial samples. And I've just placed that functionality here in this one function. So we've got the inputs X, Z, I, which are all the same as is defined in the method. And then I have this Boolean plus that just determines whether we are talking about the subscript plus I or minus I. So we can run that definition. The next function, reverse ordering, all this does is that it rearranges the ordering of the features before they're fed in to our model at the end of step 2. This is step 2F, and this just makes sure that we maintain the same ordering whenever we feed data into the model. So we can define that function, and then basically the rest of the magic is done here in approx Shapley, and we're just iterating through the entire procedure here. Most of this should appear quite similar. I tried to keep the naming of the variables as similar to the method as possible. So here we're just going to iterate over this whole procedure m times. M is one of the inputs that defines the number of iterations. And then we select our random sample, and that's Z, and we do a random shuffle, which is just defined by O. And then I reorder the samples. I construct new samples by making calls to construct sample. And then I get model predictions. And of course, for the input there, I have to use the reverse ordering function to get the data properly ordered. And then I compute the phi's, the phi values, and sum them. So that's everything that's going on in this function. So now that everything is defined, let's actually work through a manual example just by going through these different cells. So the first thing I'm going to do is take out one sample from our data. That's going to be x1, and that'll be our sample of interest. I'm going to set the number of iterations to be 100. That's just a choice that I'm making. And now let's compute the Shapley values for this sample for each of the possible features that I could compute a Shapley value for. So we've got 3 predictor features. We're going to compute 3 Shapley values. So this is for the first feature, the second feature, and the third. Note that, I just said first, second, and third, but really the features are labeled 0, 1, and 2. So you can see here that it's feature 1 that has the largest Shapley value by far. Feature 0 has, it's a much smaller value, but it's not as small as feature 2. Feature 2 basically seems to be the least important feature in these data. And we can just visualize these results by making a plot. And here you can really see that feature 1 is the one driving the show. Now you can say, okay, well, this is all good, but we're only looking at one sample. What do the Shapley values look like for all the samples in our data? Because that would probably give us a more realistic feeling for which features are really driving the behavior in the model. So, okay, what we can do is iterate through all the samples we have in our data and then compute Shapley values for all the features as well. So that's what this next cell is going to do. We're going to compute all possible Shapley values and pool them together. So we can take care of that quickly. And now let's plot the results. And here we go. So this is just a histogram, and we've color-coded the Shapley values for each of the different features. And just the magnitude, the absolute value of the absolute Shapley values is what is going to tell you the relative importance of that feature in this data. So you can see from this that the biggest spread is happening for feature 1. It has the largest absolute Shapley values. And then that's followed by feature 0. So you can see feature 0 also has a big spread, but more of it is concentrated around 0. Yeah, and it doesn't spread out quite as far as what we see with feature 1. And then feature 2 is really much more closely packed together towards the center, towards 0. And so this paints a picture that for these data, what's really driving things is feature 1, and then followed by feature 0, and then the least relevant or the least important feature is feature 2. Now, because we standardized our data to begin with at the start of this analysis, we can actually look at the coefficients in our linear model to get another check for which features should be more important and which features should not be. And that's just because with a linear regression, the relative importance of a feature will be reflected in the model coefficient. So let's take a look at this. And you can see here that, yeah, okay, this pretty much matches up with what we see with our Shapley values. So feature 1 has the largest coefficient, and this is followed by feature 0, and then feature 2. So this concludes the video. I hope that you enjoyed this, you learned something, and yeah, you got some value out of it. If that's the case, please like, share, and subscribe. Your support is greatly appreciated. And of course, if you have any questions, you can always leave a comment. So in any case, have a great day, and I will see you in the next video.